2, 1, 0. Current trial. 5, 4, 3, 2, 1, 0. Voltage now is 7.56. 5, 4, 3, 2, 1, 0. Current trial. 5, 4, 3, 2, 1, 0. Voltage now is 7.56. 5, 4, 3, 2, 1, 0. Current trial. 5, 4, 3, 2, 1, 0.
You have just seen the experiments I have made with the world's first internal force engine, or rather, the amoeba of the world's first internal force engine, whose later descendants will one day take humanity to the stars. Well, we have only traveled 30 millimeters, but you will agree that perhaps that had there been no opposing friction, then the whole system would have gone on and on and on till the end of time, or till it was stopped by some entity. Well, I have plotted, in the next few videos you will find, I have plotted the movement of the armature and the system over 2 millisecond intervals using Windows Movie Maker software, and made a series of graphs with them. I'll be explaining them in the next videos. I'm sure that if you take the original videos which you have just seen about the internal force engine, you could reproduce the same graphs. Well, this is about, well, as you see, these are two graphs for the experiment which we had just done relating to the performance of the internal force engine, or the new kind of electric motor. So let us explain the scale. So this is the time scale for both, and they are at the same, this is for the 2500 milliseconds. So what is happening is that this line, it represents the movement of the armature for the non-current case as it goes down, and the scale for this is over here, and this is for the entire motor. I mean, how much it moves, and the scale for this is here. So there is the zero position for this, and here the zero position is for the armature, and here it is for the motor. So what is happening is that as we let it go from the little sort of a ramp, it rolls down, and in the process it pushes back the whole system, and then as it rolls down, this should sort of go below, but the friction is stopping it, and so it remains steady over here till it hits the other end, and then the momentum pushes it forward. So there is a net displacement because of the fact that friction had stopped it from rolling further backwards. So really it should have been something like this had there been no friction. It should never have moved. It should have gone back more had there been no friction. But now let us see the case, what happens when we put on the current. Immediately we see that this, of course, is moving faster, so it covers the same distance in the less time. But what is also happening here is that once it has rolled backwards, even though it is pushing the armature forward, the system is not going backwards. So we may say that the friction is stopping here as it did earlier. But what happens is that over here, as it leaves it, we find that there is already a sort of force here. So before it hits it, it also moves forward. So it is like the force is pushing it forward. So when it does hit it, it also it also moves back. And then we will be finding how much is the difference between this, and that we find out from here is quite significant. Some 30 millimeters we have moved. This will be more evident in the later graphs. But what is interesting here is to see this rise in this period. That means something is pushing it forward, which is not the case here when it is a non-current case. And so we find that this indicates that there is a positive force pushing it forward, which ultimately gives a net displacement of 30 millimeters. So those are the same graphs. Now we are doing it for the non-current case for the armature and for the current case for the armature, how it has moved over the same time. They were different experiments, but now we are superimposing them, and we find obviously here that the same distance has been covered in the current case in a shorter time, which means that it is moving faster. Fair enough. But here we find that there is a clear difference between the net displacement between the current and non-current cases. Like when you are putting on the current, it is moving forward by this distance more than it did for the case when it was purely the non-current case where that gravity was pushing it forward. And here both gravity and the electricity have combined to give a net displacement of 30 millimeters or so. And that is an amazing find, because it simply violates inertia. Because so far as the system is concerned, it should not matter whether you are giving current or not giving current. What should matter is exactly how the forces involved. So with internal forces from the power pack, we are giving a net increase in displacement because of the fact that there is nothing pushing it backwards, as we had seen earlier from the pendulum experiment. So here we can say that, okay, they are not going backwards because of the friction, even though friction did not stop it from going backwards when it was rolling, but down the slope here it did go back. But what is happening here is that because of the fact that it is hitting it with a greater velocity, the whole thing is moving forward, which means that we are here breaking the first law of Newton, as we had broken the third law of Newton in the pendulum experiment. We have done a number of experiments, and these are the data points. This is the distance which it has net displacement, and this is the current. So as we see, the current is increasing here, and the more we increase the current, as we can expect, the displacements with respect to the non-current case, as we have just seen, it simply increases. And why is that? That is because the theory is that the force is proportional to the square of the current multiplied by some constant. And this graph, when you regress it, it shows a square value over here, which shows that yes, it is varying as the square of the current. But of course, there's only the displacement, not the force. So the formula for the displacement and the force is d is equal to 0.5 into force into t square. Now, if this is constant, which is not necessarily the case, and that causes a lot of fluctuations, but on the occasions where it is more or less constant, then d does vary directly as the force, and the force varies as the current. So we are getting a quadratic relationship. That is to say, the displacement varies with the square of the current, and that is very, very important in our design, because if we say increase the current in a system 10 times, we will increase the force 100 times, and that is just wonderful, as we shall see when we do some further analysis. Just remember that this varies as the square of the current, and we will also derive the formula for the force being proportional to the square of the current. I'm sorry for the poor presentation. I mean, it's too dark, and this is the best my printer could make. But well, now we have been talking about spaceships to the moon, and let's see how our experiment with this setup can be modified to be a spaceship to the moon or the planets, or even for better jet engines replacements. And now, well, it is like a two-stroke engine. Now what is happening here is that on the first stroke, the switch is on, and this moves with the force from the electricity, from the electric current, and hits this, and the whole system moves backwards. In the second, but as it leaves the rails, the switch goes off. So when it comes back, it will not experience any forward force. It will simply roll back, hit this post, and that is the second stroke. And after hitting it, when it comes and sits on the rails again, then the switch is again on, and the first stroke is continued. So this happens all the time. Of course, in this situation, we don't have what is the basics, but we do have the power source and the switch, and of course the armature, which is heavy, and the rails, and the two springs which go backwards and forwards. All we need is a permanent supply of power and a very good way of regulating the movement of the rails. And of course, instead of manually switching it, we need to have a proper electromechanical switch, which is also lossless. But basically, this is a two-stroke engine. When there is a current on, there is a forward stroke, and the armature hits the front block with high speed, and then it switches off, and it comes back when there is no voltage across the rails. Okay, so this is the same drawing, but here we have to use a bit of imagination. Let us see. Now this armature, for instance, it is round, but that won't do. It has to be sliding. So it has to be a kind of a block, and I think this will have to slide. That means that the contact should be liquid, and therefore the contact between the rails and this armature has to be done in a very careful and interesting and novel manner, not the way it is happening now, obviously. Rails, obviously, they have to be much bigger and separated by 5 meters. And the front block, well, it has to be a spring or some to push it back and absorb the very heavy impact of the heavy armature. And now the rear block, of course, another spring here, so when it comes back in the other second stroke, it will absorb some of the stroke and push it backwards with a certain velocity when the switch kicks in again. And this is the electromagnetic switch for 1 million amperes, which is something terrific. And this is a 30 megawatt generator. Just think of that. A 30 megawatt generator, which means 30 volts and 1 million amperes. And with our present technology, it should be composed of fuel cells. So we have to use our imagination to see that this is going to become the amoeba, actually the amoeba, yes, for a much more powerful internal force engine. Now this has moved it by a distance of about 30 millimeters in our first go. We hope to do a lot better than that. We hope to go to the moon in a matter of hours with our far improved prototype. This may look like a very strange drawing, mainly because I have not put any thing to note what is what over here. But this is, as I say, the highest level drawing for the internal force engine. Now, whether it is going at 1 million amps or 1 billion amps or 1 trillion amps, the basic idea will be the same. These are the rails. Now for a million ampere engine, and they can be copper, a very thick copper, but for a billion ampere, who knows what they may be. They could be streams of ions or whatever, and I just don't have any idea. But this armature, well, as we know, this has to be pretty heavy, order of tons. In fact, it will carry the entire fuel, the hydrogen, the oxygen. So the hydrogen and the oxygen, they will go in pipes to this bank of fuel cells, and there are some 30 or 40 tons of them, and they will convert the hydrogen and oxygen into water and electricity. The water will go to this pipe back to the armature. So the fuel will never be weight-wise increasing or decreasing, because all the hydrogen and oxygen will become water, and the mass of the armature will remain the same. Nothing will be exhausted, nothing will be lost. So all this current will go to a switching system over here, and there should be two sets of rails for increasing the efficiency. So the switch will, when the power is on, it will be off for the other set of rails. So this depicts that the armature has come from here to here, or it will be going from here to there. So there is only one armature or one set of rails, but there could be two sets of rails to increase the efficiency, because the power is sort of not used when it in the second stroke, when it is coming back. So we could have another set of rails. And these are the springs. The first one, it takes the full impact and then sends it back. And the second one also, absorbs it and sends it back. So the whole system moves due to the thrust given to the armature, so long as the current is on the rails. Now that is important. So this is the general principle. Now it doesn't matter whether it is millions or trillions of amps, the force will be the square of that. Immense amount of forces will be generated when you increase the current to, say, 1 billion or 1 trillion. That's unthinkable at this stage. But what I'm trying to say is that right now we have fuel cells and they are going over here, but later on we could have a nuclear reactor or something here which will generate some electricity or something, which will go to some kind of a system here which will provide the current. So the whole nuclear reactor with its mass can be going up and down over here. Or it could be that it could be generating some heat over here from the nuclear reactor, and this could be some kind of exchange from where the electricity is generated. Well, big idea is that when we do have our fuel cell, this should be pretty flexible, all the pipes, the hydrogen pipes and the oxygen pipes, so it will go backwards and forwards with two different sets just to increase the efficiency. Maybe three, who knows, I don't know, but this is the basic configuration.